And share my screen. Okay, can you see my screen? So we left off talking about the system level design considerations. So we'll move into detailed design. So this slide is referencing another presentation that I give, going over all the different kinds of parts that will come across in designing robots. This slide here is just showing the screws, but I'm going to start with this intro to robot parts presentation once we get through this slide deck. So that's kind of what we'll transition into. We'll come back to this. Just another slide showing different things. More of the same. All right. So something that we use a lot in FRC is computer-aided design. We've spoken about this a little bit. Our team in the past has used SolidWorks, but about 4 years ago, we switched to Onshape. And definitely what we recommend to the Richardson team. The great thing about Onshape is a lot of the, not all, but a lot of the files for parts that we use are already in Onshape. And so you can just add them to your robot assembly and just takes, a few seconds. In the past, this was a more involved process. You have to download the file from the vendor's website and convert it on your personal computer. And then it's only there for you and not for everyone else on your team necessarily. So CAD is a tool. It's an important tool. And if we use it correctly, it'll definitely speed up our design cycles. It'll make assembling the robot easier because everyone will just be able to hop into the CAD and see what needs to go where. A lot less questions when things just aren't living in someone's head. This is another presentation. I don't know that I'll give it, but I can definitely point you to it. This is, I call it Intro to Robot Mechanics. It is about kind of the physics behind everything that we do in robotics. So a little bit more math-based than what we normally talk about. So it's a pretty good introduction. And if people have interest in it, I can either give it or just point you to where it is online. Motors are really important. We use a lot of them on the robot. They're the main actuator that we use. Electric motors behave, for the most part, pretty linearly. The data shown here is some of the motor specs that you would see for any motor. Free speed is how fast does the motor go? How fast does it go when it's not turning anything besides itself? The free current is the amount of current it draws while doing that. And then the stall torque is if you were to put so much torque on the motor shaft that it couldn't turn itself, that would be the stall torque. And the stall current would be how much current it's drawing when that's happening. So it's not spinning at all. The motor is putting all this power into turning it and it can't turn it. So at 2.41 meters and 131 amps, which is a lot of current, you would be able to stop this particular motor called the sim motor from turning. To the right, we have a graph showing not just its performance at 2 points, the free current and the stall current, but over the full range of motion. So we have torque along the bottom. On the right, we have current. So at a speed of 0, it has this much torque because that's stalled, so we're not letting it spin. And it has this much current at a torque of 0, so it's not turning anything. It has a really high speed, turning at 50, 300 RPM, and it draws relatively little current. And so normally we're not at either one of those conditions. We're somewhere in the middle. And understanding these performance curves and how to read them, we can use that as a powerful tool for designing our robots. So we design our mechanism knowing what we want them to do and how much torque that requires, because we're trying to move a certain mass at a certain speed, or we want a certain amount of acceleration, or do something in a certain amount of time. And we can kind of back calculate what our gear ratios need to be. So we don't really almost ever, except for maybe when we're making shooters, want really high speeds. So we use gear ratios, gear reductions to bring the speed lower, which proportionally amplifies the amount of torque, which is the amount of force that rotational force that the motor can put out. So there's a lot more to it than that. And brushless motors, which are the motors we use now, are a little bit different. Richardson will probably have a little mix of both brushless and brush motors. No, Stuart says no. So just
I hear that the kit of parts this year might be a little different in terms of motors.
Got it. Okay. So you won't use a sim motor on your robot, probably. We'll be using Neo motors. But we'll talk about that at a different time. But at the end of the day, a motor is a motor. It goes at a certain speed. Some are faster than others. And just knowing what motor you're using is important to calculating what gear ratios you want to use. Pneumatics are the other type of actuator that are allowed on FRC robots. We have a picture of one here. The inside of a pneumatic just means air. So we're talking about compressed air and using compressed air to move this piston in and out. So if you put air in the back, it moves forward. If we put air in the front, it moves backwards. And we can attach things to the threaded portion at the tip of the rod and move things linearly with potentially really high forces. So the larger the piston is, the more air, because it's the force is the pressure of the air, which is 60 psi or lower, multiplied by the area, the cross-sectional area of the bore of the cylinder. And so small packages can get some really high forces, which are good. The only downside of using pneumatics is that in order to use pneumatics, you typically want to have an air compressor on your robot. Those can be kind of heavy. And there's just kind of an initial entry weight that you have to tack onto your robot before you use pneumatics. So if we only have the need for like one cylinder on our robot, that usually isn't enough of a reason to add all that extra weight to our robot. So we might say, well, how can we do that with a motor? Because there usually is a way, it's just a little bit inconvenient. But if we know that we're gonna have, 2, 3, 4, 6 cylinders on the robot, then it's definitely worthwhile. So FRC actually puts out a pretty good pneumatics manual that I'm linking to here. And there's a lot of math you can do as to like how much air you want to store on your robot for how many actuations you expect to have during a match, so you don't run out of air. And there's some details on that in this other link. One of the calculators I shared at the last presentation had another calculation for this sort of thing. So pneumatics are pretty cool. Does anyone have any questions on motors or pneumatics? 'Cause those are the two main actuators that we use in FRC. And I know that pneumatics are new to all the students because we haven't put them on a robot in a while. All right. And as you can see in this presentation, I'm like taking entire topics and just like putting them on one slide. So each of these deserves a presentation of its own. But giving you a taste of it will give you an idea of what you want to learn more about, and we can point you in the direction to learn more about those things. So drivetrain is the most important part of your robot. If you can't get from point A to point B, then you're not going to have a good time. Definitely recommend keeping your drivetrain simple, keeping it robust. Using the kit of parts chassis is one really straightforward way of doing that, and definitely the way we want Richardson to go. It's going to come in your kit of parts, and you just have to, size it and assemble it. Pierce's team has moved on to a custom drivetrain for some pretty straightforward reasons. Mounting to it is a little bit easier. We can pick our size and our wheel locations a little bit, make them a little bit more custom. And we can just really have a bit more control over how it integrates with the full robot instead of trying to fit the robot to the chassis. But, I always question, whether it's worth it. Sometimes I want to go back and other times, I like having the customization that we get with the custom chassis. So as you're considering the drivetrain, sizing it, the gear ratios that you're using, the wheels, that's really game analysis. So is the field really wide open? Are you going to be able to have long, stretches where you can just accelerate and go fast? Or are there going to be lots of obstacles like speed bumps that you have to slow down to go over if you don't want to flip your robot or break your robot? And then once you know that, what positions on the field you're going between the most for your cycles, then you get into calculating, exactly the best gear ratio and motors for that specific A to B travel. Wheel size and wheel type is really kind of tricky. If there's any like bumps or ramps on the field, it kind of forces you into a bigger wheel size. The field's flat, you can get away with a smaller wheel size. If you are, hold on, Rain has a question. Would you ever consider mechanism for FRC? No. So mechanism is a style of wheel, for those of you that don't know, that allows you to go sideways. It works really well in FTC. FTC is not the same. It really, reduces your traction on the field. So
yeah. So in general, mechanism wheels, if you just do the dynamics of it, your power in any given direction is halved, period. For FTC, where there are tons of rules against defense and tons of rules against robot-to-robot interaction, and there's not even tons of rules, but the games and designs of it's kind of dumb. Yeah, it's fine. For FRC, where defense is generally a thing where there is a lot of robot-to-robot interaction, and where even though you may not want to run into another robot because it slows you down as far as your cycles, you may have to run into a robot. And in that case, you want to make sure you have enough power going in the direction that you're going and not being divided out by vector summation. If we were to ever want to go sideways, I would look more at this point in time, I'd look more at swerve style than mechanisms.
That was fun.
Hey, Alexa. Um, we just started talking about drivetrains. So the good thing about using smaller wheels on your robot as opposed to bigger wheels is that you get to use a smaller gear reduction for a smaller wheel, which just reduces weight kind of all around because your wheels are smaller, so they weigh less. Your gears are essentially smaller and weigh less. If you can get rid of an entire stage of your gearbox, that could be advantageous. Most teams run either 4 or 6-inch wheels. Sometimes if the field is like really full of obstacles, you'll go, 8-inch pneumatic wheels. The pneumatic wheels are like your car, so they're actually full of air, and they can kind of act as a pseudo suspension because they absorb some shock. And so those have advantages. I think the last time anyone really used them was 2016.
Yeah, you saw some of them in 2020. It wasn't absent because of the barriers.
That's true. Yeah,
but it definitely wasn't the the kind of everyone was using them.
Yeah, and they're kind of fun too. And then in terms of like quantity of wheels, like the kit of parts designed to be 3 wheels on each side. With our custom drivetrain, we can, do 2 on each side, 3 on each side, 4 on each side. And we just have to look at the game to see what that would look like. There's advantages and disadvantages to each. There's no one that's better than another. It's just like, where's your center of gravity going to be? What sort of ramps are you going to have to go up to? There's a whole lot of math behind, drivetrain design. The next bullet point, traction limited. So your field is typically carpet. We have wheels that are made out of different materials with different treads. There's a coefficient of friction that's associated with that. And we don't want the robot to basically like break itself trying to move. So we try to make sure that, like, if you were to drive up against the wall, that your motor would have enough power to keep the wheels just like spinning in place instead of stalling out, because that can draw a lot of current and break your robot if you aren't taking that into account. So it's just another consideration. Something that you will see, but see less of than in the past, is shifting gearboxes. Shifting gearboxes allow you to have 2 speeds or 3 speeds. You have basically pneumatics that shift from different gear sets to change the ratio. And the advantage of that is that you can go into low gear to get high traction, or high gear to get faster accelerations and speeds. The question is like a bike, and yes, it's exactly like a bike. It's like your car as well. You have a transmission. You probably have 5 or 6 different gear ratios that your car is switching between. When it's just starting up, it's using a lower gear to get higher accelerations. Then as you get faster, it switches to a different gear ratio to lower the work that the engine's doing. The reason you don't see it as much anymore is that the newer motors are just so powerful that you have the power you want no matter what. But definitely teams that are optimizing certain things will still use them. They add a lot of complexity to your drivetrain, which, since your drivetrain is the most important part of your robot, we tend to avoid adding complexity where possible and keep things simple. This is JVN's mechanical design calculator. I'll go ahead and open it and show it to you. This is going to be an old one. Actually, maybe I'll grab one from our old stuff.
John, I hope you're not messing with one that I'm messing with right now.
I'm not going to mess with anything.
No. I've been screwing around with our calculator.
Okay.
This one looks fine, probably.
So yeah, so here's, this is actually showing our gearbox that we use for our custom drivetrain. This is not right. So here you have a selection for the different motors. So you can pull in the motor data. So I'll pull in Neo motor, which is what we like to use, and you can see that the speed and the torque's updated here. So this is just showing you what they are. These constants are just efficiencies. We don't typically touch them. The numbers are just a guesstimate. They're not right. They're just taking into account the fact that you don't have 100% efficiency. Talking about efficiency, all that means is that when you're moving things around, there is friction like between gears that is turned into heat, and that heat is lost power like directly. Because if it isn't going to your mechanism, it's being lost as heat, either in the motor itself or in the components, the bearings and things like that. This next line is asking how many gearboxes are on your drivetrain. We have one on each side. How many motors are in each gearbox? Here we have 3. The total weight's going to play into this because that's what we're moving around. We're moving our robot around. And here we're saying that all the weight is on driven wheels. Sometimes you might make a design decision to not power all of your wheels. So say you have 4 wheels and you're only powering 1 on each side, and you would reduce this then to like say 50% in that example.
So one thing I do want to point out here with the total weight, when we're designing the robot, the weight of the robot is 125 pounds. Right now it's currently at, or we're expecting it to be 125 pounds. That is without the battery, and that is without the bumpers. So the robot weight, the total weight here needs to include the bumpers and the weight and the battery. So just as you're doing that design, don't think that, okay, I got a 120-pound robot, I'll type on 120, and that's the number. There's additional things that need to go into this number, that even though your total robot, you're working towards one number, this number needs to be different.
Right. And some teams will deliberately target like really light robots. So they might be putting like 80 in here. So it just depends. You really have to know what you want to do and know what you're doing to use these calculators effectively. Here we're putting in different wheel diameters and the coefficient of friction. Typically, if you're buying a wheel, especially with the FRC vendors, it'll tell you what the coefficient of friction is. That's not always true. And then the last part of it is, what are your gear ratios? So here we have 2 separate stages. So we have one stage where our motor has a 12-tooth pinion gear on it, driving a 64-tooth gear. And then that same shaft that has the 64-tooth gear has a 32-tooth gear on it as well, which is spinning a 52-tooth gear, which is directly driving our wheel. So with this combination, we're seeing total reduction of 8.67. So our speed is reduced. You could literally divide this by 8.67, and you could multiply, well, you can multiply your stall torque, but any of the torques would be multiplied by that ratio.
Minus your efficiencies.
Correct. Efficiencies don't play into speeds, they do play into torques. The speed that we're going is 17.15. That's assuming we get up to the fast speed. If you're just going, 5 feet, you probably don't have enough time to accelerate to that speed. But that's what it is. This adjusted speed is kind of like the fudge factor that's taking into account the speed loss constant. And it is, so you're going to be somewhere in between these two probably. But the real speed is not always going to be exactly what the calculator tells you, I guess is the point.
I think the adjusted speed is actually what it's loaded down. The free speed is if you have no weight on it.
Oh, got it. I think that's right. So yeah, so we're looking at something around 13, 14 feet per second. The amperage, this is the current draw. So we're drawing a lot of current here. This is probably too much. Our biggest breakers are rated at 40. You can kind of go above it for short periods of time. And playing with these gear ratios, playing with the weights, playing with the wheel's diameter will change these. So if we go to another 64 tooth wheel, here we just reduced our speed, but also reduced our current drop. So there's a bunch of tabs down here. They're not just for drivetrains. You might have different mechanisms too. So if you have a lift mechanism, I don't know what's going on here. But
I think this is one that I'm messing with.
that's fine.
But I did want to go back to the drivetrain there for all the teams, because I think everyone's new to robots. It's FRC robots. Generally, your adjusted drivetrain speed, you want to keep somewhere between 10 and 15 feet per second, or 10 and like 14 feet per second. Some people say 12 is the sweet spot. 14 is very fast. 10 is pretty slow. I am more of the opinion that you want to be generally closer to 10. Like I would think 11 is probably this 11.28 is probably fine. The reason being is, even though you're technically slower in sprints and long sprints, you will have the advantage if you get into a pushing match, and you're also going to have a little bit more acceleration because you're going to have that more torque in the beginning. So you'll be able to hit your kind of cruising speed faster. It's also a little bit more control for your driver, but 10 to 14 is your range that you want to be at. I've heard teams of going as fast as 17. I don't think that's really controllable. I think your drivers would hate you.
But
BattleBots, they actually they're gearing more towards 8. They push a lot more than they want to go fast.
I know this isn't BattleBots, but it's a ton of contact. It's like more like football, I guess, compared to like, I don't know, what is a BattleBots, like UFC or something. So the point is, there's calculators. I don't really want to get too much into this. Different calculators have different inputs. So this is a climber. How far do you want to climb up? How much are you lifting? You're going to have some winch or pulley diameter of a certain size instead of like wheel diameters. And it just helps you come up with answers. So JVN's a really good calculator, and we'll definitely use it for our robots. Not necessarily for drivetrain, because there are better drivetrain calculators, but for any mechanism that we really have on our robot, we'll probably have a JVN calculator tab. So I introduced this last time as well. This is actually a version old. This is the 2016, 2017 kit of parts. They all pretty much look the same. If I were looking at them, I wouldn't even be able to tell you what the differences are. They move the holes around every once in a while. It's awesome. It just works. It's a little bit difficult to assemble. And I wish they made that better. And it'll come with these Tough Box mini gearboxes. It'll come with 6-inch, Andy Marcel's high grip wheels, these white treaded wheels. The only thing I would definitely recommend adding to it is a belly pan. Belly pan is just a piece of material that just rectangular or square, and it goes it goes between the sides and between the corners, and it really keeps your robot frame stiff, and it doesn't let it parallelogram out of shape. So we can talk about that more when kickoff comes, because you'll definitely want to put one on your robot. You can make them out of wood, you can make them out of plastic, we typically make them out of metal just because it's the material we have around, and it's heavier, but that's okay. We went over this. I'm not going to go over it again. This is just explaining. If you're looking at this presentation, you can come back and see what the different boxes do. Here are a bunch of drivetrain resources. Because drivetrains are kind of the one constant from year to year, they've definitely been explored in great depth by different teams and mentors. There's always presentations, new presentations on drivetrains. Some of these go back to, 2007 and earlier. Drivetrains were a little bit different. The kit of parts was different. But yeah, anything by 11, 14 is good content. Yeah. So drivetrains are the most important part of your robot, but you need mechanisms to get points usually. Minimal points just driving, but there are sometimes some. You have game objects that you need to acquire, you need to manipulate them. So you might need to move them around within your robot. You might need to store them in your robot. You might need to lift them to a certain position or rotate them to a certain position. And then you need to release them. And so how you do that is really the challenge every year. There are some pretty good mechanism design presentations. They typically are just showing you all like classes of different mechanisms. So different types of elevators, lifters, roller intakes, arms, telescoping mechanisms. And in order to get into the nitty-gritty detail, that's when you need to probably start looking at Chief Delphi, looking at threads where people are actually explaining in detail a specific robot, looking at CAD of other robots, because no one's going to tell you exactly how to design what you want to design. You have to, learn as much as you can and then change what you need to change to have the effect that you want. This is kind of wrapping up the presentation. Making assumptions is a really big deal for engineering in general. In order to engineer effectively, we have to make assumptions. But if you make bad assumptions, it can really bite you. You know what they say about assumptions, right? Anybody? Assumptions make an ass out of you and me. The bad thing is to say, the bad thing is to say that, you understand how something works and that you're not going to test it, because that's when you break on the field. It definitely happens to us more than I like to admit. But we definitely want to test every scenario. We want to test it like it's a practice. So we want our drivers, not looking over the robot as they're moving the controls, but we want them back behind the driver's station just so that they are getting used to lines of sight. They're getting used to really what a match will be like. As we prototype, some things are going to work better than others. Usually we'll have different aspects or different prototypes that we like. And the goal would be to combine those things that we like together to create the best design. Building flexibility into your designs, literally and figuratively. So literally, one of the things that is definitely important is to understand that you're going to be in this really like head-to-head competition, lots of contact. Your robot needs to be robust. It needs to not break. And in order to not break, sometimes that means you want your mechanisms to be able to flex so they absorb the impact, as opposed to something being super rigid, getting hit with a force that it can't absorb. And when that happens, it'll just break. Maybe it doesn't break, the first 10 times that it gets hit, but it breaks that 11th time. And so one of the things we do a lot when we have mechanisms that extend outside the robot is we build them out of polycarbonate, out of a plastic that is really has really high impact resistance, and it will flex a little bit. It might look a little janky, but it's really purposefully designed that way. And then the other side of flexibility is knowing that we're going to be iterating. We really want to be able to switch our mechanisms out pretty quickly. So finding some modular way to design how a mechanism bolts on will really allow you to get things on and off the robot faster, which makes the drivers happy because they have more time driving the robot. It makes you happy because when something breaks in competition and you have a full spare mechanism that you can bolt on, and you don't miss your next match because you're having to fix the robot just because you made it so hard to attach. The other side of flexibility that is really easy to miss is that since every mechanism and every game piece has tolerances, you can't rely on exact dimensions for a mechanism to work well. So in order to get around that, we look at this idea of flexibility or compliance. So if you have a squishy ball, for example, you can rely on that ball to squish a little bit as you bring it into your robot, and you can have a pretty rigid mechanism knowing that the ball is going to take up that tolerance that I'm talking about. But our game pieces aren't always squishy. Sometimes they're really hard plastic or other material. And if that's the case, then we want our mechanisms to have that compliance. So maybe you have, your intake spring loaded. So you have wheels that are being kind of held together with a spring. And then as the game piece comes into the robot, it spreads them, and that allows the wheels to remain in contact with the game piece. So what I want you to take away from that is hard game pieces, compliance in the robot, softer game pieces, compliance just in the game piece. And you can either have compliant mechanisms or have rigid mechanisms in that case. The next bullet point, don't integrate your subsystems too much. It's really pretty awesome when you see a robot that has really done integration well. And it makes it, very sleek, very beautiful. Maybe it uses fewer motors than a different design that's less integrated. But it takes more work to get to a well-working integrated, two subsystems that are integrated. And so every time you change one, you're essentially swapping out your other mechanism as well. So it's a hard line to know where the line is. But for our team, I definitely want to err on the side of not integrating subsystems if we can. And sometimes it's easy and sometimes it's not. Like this past robot that we built in 2020, we had our shooter, and then the only good place we could find to put the winch for our climber was on the same shooter plates. And while it packaged really nicely, anytime we wanted to make a change to one, we had to change the other. And our first plates that we made, the holes for the climber weren't actually, for the winch weren't actually put on. And so our practice robot couldn't even have the winch, which had other bad effects. So you definitely kind of learn pretty quickly that integrating things can bite you, but it's very tempting to do. Be careful with your robot. A match is only 2.5 minutes. That's what your robot needs to be able to handle. If you're just driving for hours on end at the shop, you know, your air compressors can burn out, your motors can burn out. We just want to be really cognizant of how hard we're running the robot, because we want to protect those. They're important parts and they're expensive parts. Does anyone have any questions? That was a lot, and at the same time, it was really vague. The hard part about robot design is that there's just so many topics, and you can talk, you know, for hours on any one of those individually. I sent some of these resources out from the last presentation we gave. I put them in Slack, but here are even more. This presentation was put together in 2019. I hope all the links still work, but I don't guarantee it. The team sites you see here, good resources. 973 had and 610 have pretty good CAD design tutorials. They're done in SolidWorks, but most of it's transferable. 1678, they're one of the best teams in the world. They do workshops every fall and they post their presentations. So like every fall, there's like 10 new presentations on their website. And then the 3847, that was Team Spectrum. I showed you their website last week. And then these are more like kind of official. The FRC has their own mechanical resources on their website, different topics. Chief Delphi we talked about. Blue Alliance has a blog that we didn't talk about, which I don't know if that gets updated very often. WPI has a lot of programming resources, which your programmers will definitely get familiar with WPI. COTS stands for commercial off the shelf. That just means our vendor purchase parts. These are people we purchase from. We very rarely purchase from companies other than these. And this find robot parts is pretty helpful. You can just go in there, say you want a gear of this size, and it'll point you directly to like Andy Markrev specs, like exactly what the part number and the link to the part is. Yeah, so if there are any questions, I'm gonna move on to this other presentation. So this is a pretty big change of pace. We're gonna start talking about actual parts that go on the robot. I think that personally, you know, as I, you know, have developed as an engineer, one of the things I've realized is that if you don't know something exists, it's really hard to design with it, whether that's a specific part or a manufacturing process. So you always come across new things and be like, oh, well, I wish I knew about that. I would have used this on this project I did, you know, 5 years ago. And this presentation is a really good introduction to the parts that we will be using on our robots. I'm going to skip the table of contents because we're just going to go through all this. Raw materials. So at a very bare level, we'll be using different types of metals, different types of plastics, essentially wood. There'll be parts that are made of rubber, parts that are, I guess that's mostly it. But material properties are a thing. We don't really get into that in FRC, but you will get into it if you become a mechanical engineer. You'll have whole courses about it in college. We use a lot of aluminum and plastic. This list is just, important material properties. You have your strength, your weight, your elasticity, and hardness, impact resistance. How machinable is it? Is it easy to machine or hard to machine? Is it just gonna rust on your robot? How corrosion resistant is it? And then if you're working with electronics, like what sort of conductivity does it have? Which also plays in electrical conductivity and thermal conductivity go hand in hand. Typically, if you have material that's good at one, it's good at the other. So we use a lot of aluminum. The grades of aluminum alloys that we use are 60601. That's very general purpose. A lot of the tube that we use, actually all the tube that we use for the most part will be 60601. We'll make a lot of gussets and plates out of 60601. If we want a bent sheet metal part, 60601 does not bend well at all. If you don't bend it with a very large bend radius, which is difficult to do, it's just gonna break on you. Or if it doesn't break, when you bend it, it'll break on the field. The unfortunate thing is it's very hard to tell the difference between the two. So I know that we have some in our shop that's all just like stacked up together, and I honestly couldn't tell you what is what unless it happens to be printed on the material itself. 7075 for what we use it for, it's like what's considered like a aerospace grade alloy. It's more expensive and it's higher strength. For FRC applications, most of the hex shaft and thunder hex shaft that we use is made out of 7075. So aluminum is great because it has pretty good strength to weight ratio for the sorts of conditions we put it in and on the field. Steel is stronger and more heavy than aluminum. It also is harder to get corrosion resistant steel, and it usually needs a coating of some sort. Stainless steel is more corrosion resistant. It's also tends to be weaker. It's really difficult to machine. And some grades of stainless steel are non-magnetic. So corrosion resistant means how well it's basically going to hold up to water and the humidity in the air. So we have like black oxide coated steel screws in the shop and like zinc coated steel screws in the shop. And you can see like on our 2020 robot, like our shop doesn't have great humidity control because it's just open a lot of the time. You can see rust on those screws. So that's what corrosion resistant means, like it's just rusting. Sorry, I gotta plug in my computer.
Oh my gosh, I watched the video from like last week and I saw there was like one moment when Ricky was like, oh no, my computer. And then you were like rushing and I was like, go Ricky, go. I was like cheering for you so much.
Thank you.
Welcome.
Yeah. The problem with my computer is when it tells you the battery's low, you only have like 10 seconds to plug in the battery, the charger, because it's stupid.
That's how my like Zoom classes were at the beginning of like 2020 or whatever, of like freshman year. I would be like in the middle of a class, like running through my house to find a charger.
Yeah.
Should
All
blend
right. So the other plastics we use, this is a very comprehensive list of plastics we have in our shop almost at all times polycarbonate. We love it because it is very impact resistant. It's transparent, so that's fun. We have it in different thicknesses. We have 1/16 inch, 1/8 inch, and 1/4 inch. We can laser cut it. It kind of burns, but we can laser cut it. And then if you want to, you can also bend it, kind of like sheet metal, which is a really cool property. This first bullet point, acrylic, unfortunately, it also exists in the shop because the classes use it and it laser cuts really, really well. But don't ever, ever, ever put it on a robot. It will shatter. It looks like polycarbonate, but if you hit it with a hammer, it will shatter. So be very careful. If you're gonna make something on the robot, hit it with a hammer first. Not encouraging you to destroy material, but it wouldn't be good if it ended up on the robot. ABS, we probably won't be 3D printing with it because it's more difficult to 3D print.
We actually left over from, I think, 2019. We have a 3x3 sheet of 1/4 inch ABS somewhere in the shop. It's black. I wanted to test it out with something. It's what most, if you think of like most housing on electrical components, or most like consumer, like on this battery, this is ABS. It's a lot of times people think it's 3D printed, and it is. But when you make foreign plastic shells, 90% of the time it's ABS.
Yeah, ABS is super common, very general purpose. It has decent mechanical properties. And yeah, like Stuart said, like if you have like a plastic thing in your house, it's very likely to be ABS. And so because it's common, it's relatively cheap as materials go. HDPE, it's high density polyethylene. I couldn't tell you what ABS stands for. HDPE is usually like whitish. You might have like cutting boards made out of it. It can be pretty easily machinable, and it's like on the borderline of like starting to be low friction. PLA is a very common 3D printer material. It's not very common outside of 3D printing. It just, I guess, happens to have a pretty low melt temperature, so people like to use it to 3D print. So a lot of the time, what we will do, so we have two types of 3D printers, the printers that print, like the hobby grade printers that print the PLA, and then we have the Markforged printer, which prints in a material. It's like a composite material called onyx, which is a lot stronger than PLA. But because we know we're going to iterate parts, we want to print them in PLA first, iterate a couple times, so we know that it's good before we print them in the better but much more expensive material. PVC, it's in this presentation because some teams use it. It's not very strong. It's not very impact resistant. It will shatter. You see it used sometimes as spacers. You can cut PVC up pretty cheaply to make spacers. I don't know that we'll do it. It's also pretty easy to 3D print spacers. But I wanted to put it here because it is, you will see it on different robots. And it doesn't just come in pipes. You can buy PVC in sheets as well. So the next grouping of materials are much, or in some cases, much more expensive. Nylon's kind of less expensive, but still on the more expensive side. Acetyl Delrin. So acetyl is the material, name. Delrin's a brand name. It's very strong. It has very good material properties. It's like ABS on steroids. It's easy to machine. It's pretty low friction. It's really pretty nice all the way around. If we were to like design a part that we like had to machine out of like a block of material for some reason, it would probably be, we'd probably buy a chunk of Delrin. Nylon is kind of like a cheaper version of Delrin. It's pretty strong. It's pretty low friction. In industry, we don't use it, at least in my industry, we don't use it a whole lot because it's not dimensionally stable. So what that means is that it absorbs humidity. So like depending on like the water content of the nylon, it will like dimensionally shift just a little bit. But we're talking about like fractions of an inch. So not necessarily something that would be important on one of our robots, depending on how we used it. The next two, UHMW and PTFE, which is commonly known as Teflon. Teflon is what a lot of non-stick pans are coated with, except that it causes cancer. UHMW is a great low friction plastic. Teflon is super low friction, so low friction that it almost makes it hard to use. So it's like on our hopper, we had like sheets of Teflon that we used to keep the friction low because the polycarbonate that we made it out of isn't low friction. But just like adhering the Teflon to the polycarbonate was challenging. So you just kind of have to try different things, especially during the prototyping process. If something's not working, we'll be like, hey, let's try different material. Like maybe that's the problem.
Teflon is the anti-duct tape. If you want things to hold together, use duct tape. If you want things to never ever hold together, even though they touch, Teflon. Teflon also can be found in cans. Oh, I have one right here. We will use these cans. They're called chain savers. If we're using 35 or 25 chain, we'll use this stuff, which is essentially Teflon in a aerosolized form that adheres itself to the metal and prevents corrosion and keeps everything sliding. One problem I have learned about this stuff is it can get in, you can breathe it in and it will be in your blood forever. It's apparently a big problem. So when we use that, make sure everyone in the room is wearing a mask.
Or do it outside.
Or do it outside with a mask.
Yeah.
If you've eaten from non-stick pans, you have Teflon in your blood. I'm sorry. It just happens. Welcome to the Anthropocene.
Yeah. So microplastics are a thing too. Material stock. So we're going to talk about material in different ways based upon the shape that we purchase it in. And so when we say things are off the shelf for stock sizes, that means we go out and we purchase that exactly. So if we want like 1/4 inch polycarbonate, we go and we purchase 1/4 inch polycarbonate. We're not taking 1/2 inch polycarbonate and like machining it down to 1/4 inch polycarbonate. That's just a waste of time and materials. So knowing what sizes things come in is really good for a designer to get familiar with because they can make products that are cheaper because the manufacturers don't have to do something custom for them. But if you know that you're selling millions of something, then you can just have it made in the size you want to begin with and have a little bit more design flexibility. Yeah, so McMaster I guess I'll go to McMaster. This is kind of a rabbit hole. McMaster sells everything and they ship it to you next day. Companies love McMaster. These are just some general categories of things that they sell. We actually have a catalog. Actually, I have a catalog that I've been meaning to take to the shop just because it's fun and it's thousands of pages. But you want a screw? Well, here's the bajillion types of screws they sell, and it goes on forever. So that's a fun website. I go to it probably every day at work. So the different types of stock that we'll talk about are sheet. So most of the stuff we'll deal with in sheet or plate. So sheet, and it just depends on the specific material, like where one thickness trades off into another. So if you're looking at McMaster, like maybe sheet becomes plate, like when you get to 1/4 of an inch. Foil is like really thin sheet, like it might come on a roll. Like it's really flexible. Bars are pretty much kind of like plates, but instead of being like large rectangles, they're usually like long and narrow and more squarish. So you can get a 1/4 inch thick plate of material, or you could get a 1/4 inch bar of material, but it might only be, 1/4 inch by 2 or 1/4 inch by 6 cross section. And then we get fancier. So companies will make different shapes that have different uses. So we use rods, we use hex, which is just a hexagon shape to transmit torque. And then tubes of all different sizes and shapes. So we'll have in stock in our shop, we'll have 1x1, like outer dimensions of tube, 1x2. We'll have 1 inch round tube. And sometimes, depending on what we're buying, it could have other features. So Versa frame comes with holes drilled on 2 of the sides. And then the wall thickness varies, so that will affect how strong it is and how light it is. We also use angle a lot. We'll have that in the shop. So angle is this L shape. It is, in our shop, we have like 1 inch by 1 inch, 1.5 inch by 1.5 inch, and 2 inches by 2 inches. This can bolt on pretty easily to some flat sheet and give it a lot of strength if you didn't want to, for example, bend that angle into the sheet. C channel and U channel. The FTC students will be familiar with this C channel. Just means it's C-shaped. U channel is just deeper C channel. It has a lot of strength as well. And then fancier extrusions like the Rev 50mm extrusions, or what this is called 8020, it's a company's name, has slots in it so you can move things around. Once you bolt them, you can just loosen them and slide them down the slot. T-slot extrusion has a lot of advantages, but it has the trade-off that it's really heavy and
expensive.
Yes, expensive.
Those the tools to make that they extrude, the dies that they use, those are they have trademarks, they have patents on that particular shape, and they charge a lot of money for it.
So does anyone have a question on just raw material? So like I said, we'll have a lot of aluminum in the shop. We'll have different shapes, angle, tube, hex, shaft. We'll have.
And to the Richardson team members, y'all will have access, like Pierce's shop, the inventory there is essentially y'all's inventory, at least for now. I haven't had a chance to sit down and set up a full inventory for y'all, a full like on-hand inventory. So it's the same.
Awesome. So knowing the different shapes you have available to you will factor directly into your designs, because you'll be like, oh, I can take this angle and I can cut an inch off of it, and now I have like a cool bracket that I can use to attach, something perpendicular to my robot. And so you have to think what you have with what you have to design with what you have, because if you don't, then you're either going to have to spend money you don't have necessarily, or just waiting for a part or new material to come in can also set back your season. So moving on to fasteners. So fasteners, anything that holds parts together. Fastener could be temporary or it could be permanent. Screw is considered temporary because you can unscrew it after you screw it in. But something like a rivet, which we'll talk about if you don't know what that is, they're more permanent. You can take your parts apart, but you have to destroy the rivet to do that. So we're going to talk about fasteners and how to use them. That last slide is just pointing out that, glue is a fastener, Velcro is a fastener. Don't forget about that. We have other things at our disposal. And more adhesives are being used in industrial consumer products, just because assembling things is really, sorry. Yes, hook and loop. We don't use the term Velcro. So adhesives are being used more and more because it's really easy to stick two things together, and they can be quite strong. And your assembler doesn't have to sit there screwing in every little screw. Yes, Velcro is a brand. It is not, it's like Kleenex. So machine screws is just what they're called, as opposed to like wood screws or sheet metal screws. They have different shapes, different head styles. People will get really into the semantics of what different things are called, but technically, from a technical perspective, something is a screw if it sandwiches one material and goes into and threads into the lower material. That's a screw. If you put a nut on the same thing, it's a bolt. I don't really know why people get hung up on the different terminology, but I call them screws. I call them all screws. Bolt isn't in my vocabulary. If you use a threaded fastener that doesn't have a head on it, now it's a stud. You might hear those things out in the world. So these 6 styles, that's just a small selection of the different styles, but I have a slide on each one of them that we're going to talk about. Socket head screws, they're very common. They are, I guess, of these, especially compared to round head screws or pan head screws, the drive size. So here there's like an Allen key, a hex shape that we use to install the screw. The drive size of a screw is larger on a socket head screw compared to a round head screw or a flat head screw. So if you had a 1/4 inch screw you would be able to use a larger, stronger tool for the same screw if it was a socket head. We have some of them in the shop. We don't have a lot of socket head screws, but we do have some. And that hex shape, some people call the tool a hex key, other people call it an Allen wrench. It's all the same thing. And because the socket head is bigger, we tend to prefer using the round head screws. And so we stock a lot more of the round head screws than socket head screws, but not for any significant reason other than they tend to be a little bit larger, which doesn't package as well when you have limited space. Round-headed screws are great. We use them a lot. The ones that we buy have this hex key shape. Make sure you're using the right size hex key. You can strip the head of the screw, which means that you basically round out the hex so that no tool can grab onto it and it gets stuck in your robot. It becomes more of a problem the smaller you go. So smaller screws, smaller tools, closer to being round to begin with. You'll notice that for all of the FTC stuff with those small M3 screws, you don't see any of these round-headed screws. They're either socket head or they're hex head for that reason. Set screws. Set screws are basically headless. The hex or whatever drive style they have is within the diameter of the screw itself. Where we see these are on shaft collars a lot, or sometimes in gearboxes. We don't use them very often, but I know that like in FTC, we had them on the shaft collars. And always, one thing that we'll talk about is Loctite. We'll always want to make sure we're Loctiting set screws because they can come out just like any other screw. Flat-headed screws are when you want the screw head to be subflush. You can drill with a type of drill called a countersink drill bit, and it will create this angular shape. You might see these on some products that we buy, but we don't stock countersunk screws. It's just more effort for the same thing. Also, since the angles are self-aligning, if you have like a hole pattern with like 2 or 4 or 6 countersunk screws, they're all going to be trying to self-align and fighting against each other. So if your tolerances aren't good enough, you might not be able to even get it to go together properly, which is a disadvantage. So one thing that you'll find when talking about the lengths of screws, on a socket head screw or a rounded head screw, the length does not include the head of the screw, it's just the threaded portion. On flat head screws, the head is included in the length. So that's just something to be aware of. Hex head screws, also something that's really good in the sense that you can put a lot of torque on the screw head to get it really tight. We see these sometimes, like the kit apart, like drive axles are actually hex-headed screws. If you can't come in, for whatever you're designing, you can't get your tool in, axial to the screw itself. The good thing about hex-headed screws is you're coming in, out of plane, so perpendicular to the length of the screw. So you might have an application where like that's the only style of head that would work.
For those who are going to be joining us for the field build on the Sunday after kickoff, the field uses a ton of these. I had to buy so many of these hex head screws. It's annoying.
Yeah, they're used a lot in construction industry because they can use big tools and use impact drivers to tighten them and not break them. Shoulder screws are a special thing. We don't really use them as we use screws to fasten things together. The cool thing about shoulder screws is they have this short precision shoulder that you can use. So you screw this into a piece of material, it bottoms out on that shoulder, and now you have something that you could, use as a place to mount a bearing or some other thing that needs to spin. We do not stock shoulder screws, but we will design with them so we can purchase them as needed. They're really kind of, you need to buy the right one for whatever it is you're designing. And maybe it'll get to a point in the future where we do stock a couple sizes, but right now we don't. Screw sizes. So this is kind of confusing before you've been introduced to it. So when we talk about screw sizes, it's not necessarily like speaking in English. So we'll talk about the numbers. So the numbers is going to be the size of the screw. So we have like number 8 screw or number 10 screw. And then once they get large enough, they switch over to fractions. So we'll have 8, 10, and then 1/4 inch screws. And then they'll have a number after that, which is the pitch of the threads. So that is the number of threads per inch on the screw. So a 1/4 20 bolt that is 1 inch long will have exactly 20 turns on that thread. And that means it will take you 20 revolutions of turning that screw to have it fully threaded into your material. Like I said before, for a countersunk screw, the length includes the head, and that's the only type of screw that is the case for. We'll get to this on the next slide. It'll make a little bit more sense. Long screws aren't necessarily threaded the full length. And those are called partially threaded screws. A lot of the time you can, when you go on McMaster, you can purchase a partially threaded screw or a fully threaded screw. And the fully threaded screws are just more expensive because it took more time and effort to manufacture them. And the diameter of the unthreaded portion matches the diameter of the threads. It just won't have threads on it. So it'll stop if you're threading it into a tapped hole, but if you're just passing it through a clearance hole, you will not have any issues. So here's what we're talking about. So number 4, number 6, number 8, number 10, 1/4 inch. These are very common sizes. Typically on our robots, we try to stick with number 10. Sometimes the parts that we use only use number 8, so we have to use number 8. And every once in a while, you have something that uses, this is more like random off-the-shelf stuff. Some of the old control system components had, like I think the Robo Rio has like number 4 screws or threaded inserts in it. So here, this table is showing what the outside, this major diameter of the threads are. The bigger the number, the bigger it is. The head diameter is going to be important for you to know. You don't need to memorize any of this stuff. You can always look it up. But knowing that you have to take it into account. The head height will always be listed when you're purchasing screws, and then how large of a hex key you will need to install and remove it. These are pretty standard. For the routed head screws, these are the standards. Like I said earlier, if you have a socket head screw, the drive size will be different. The head diameter will be different. The head height will be different. So here we have an 832 by 1 inch it is partially threaded. The way they spec it, they say, we'll guarantee at least 7/8 of an inch are threaded, but it may not be exactly that. And so the 32 is the threads per inch. Number 8 screws, and a lot of screws come in 2 different pitch options, sometimes 3. So for number 8 screws, we have 32 threads per inch and 36 threads per inch. Since 32 is a smaller number than 36, it means it has fewer turns. And it is called a coarse thread. Coarse is not comparing it to other screws, just to the other pitch options in that size. So you'll have a number 10 screw, which has pitch options of 24 and 32. So in that case, 32 is considered the fine pitch because 24 is the coarse. And so for the screws that we stock, we'll have 832s, and we do not use 836. And for number 10s, we use 1032 and not 1024. And that's really important because if you have both, it can get really bad. You can, someone will force a screw into a pitch that it's not meant for, and they'll damage it, and it causes trouble. Here's a short list. I don't know how accurate this is at this point. This is probably 4 years old, but we try to keep a good stock, especially of these number 10s and quarter 20s. And if we need different sizes, we'll buy different sizes. Screws are not that expensive. Like a box of 100 screws, it's going to be like $5. Just depends on the size. Bigger screws are more expensive. So in terms of fastening things together, so one easy way to do it is to take the screw, pass it through whatever it is you're trying to sandwich, and put a nut on the back side. The second way to do it is to take the second piece, so the piece furthest away from the head, and to do what is called tap it. So you actually machine threads into the material itself. And in case number 1, the nuts that we use all the time are called lock nuts. So they actually have a nylon ring built into the nut, which prevents the vibrations from backing them out. If you do case number 2, where you do not have those nylock nuts, we'll use something called Loctite, which is a thread locker. We'll put it on the screw, and for metal, not plastic, for metal, it will basically dry as we're just going to finish up in a couple minutes, Rain. We'll use Loctite, which basically dries as a solid nylon and keeps your parts from not vibrating apart. One thing that's really, really, really important is you never have 2 tapped holes together. It won't work well if you are threading into the first piece of material and then the threads don't line up on the second piece of material, and you just can't ever get them tight correctly. So don't do that. In the first material that you're passing through, make it a hole called a clearance hole that we're passing it through. And screw hole clearances are a thing. You don't need to make this up. In Onshape and other CAD software, when you make a hole using what they call the hole wizard, you just select the size of screw and it will make the hole for you. There are different sizes of clearance holes. So for a particular screw, you might have a close fitting clearance hole or more of a free fitting clearance hole. Typically, free is what we want to use. There might even be an option for an even looser fitting clearance hole. And we can always use washers under the screw heads to make sure that the screw head doesn't get stuck in the hole, which shouldn't happen anyways, but washers distribute the load anyways. So
I'll just hop in here and say like some quick assembly tips. So generally, so you can tell the difference between close fit and free fit. Because it'll be harder to like push a screw into a close fit hole sometimes, especially if you have metal burrs hanging off. Also with assembly, there is a tolerance built in, so you can absolutely misalign two parts, even if like the screw is going through a hole in both parts. So you want to be paying attention to that and making sure like edges are aligned and things like that. Don't just assume like, oh, the screw has gone through my parts, therefore they are correct, because that can definitely not be the case.
For those of y'all who were at the meeting yesterday when we were assembling the perimeter, y'all got to learn about that firsthand.
Yeah, so a very common technique when you're assembling something that has multiple screws is get all the screws in before you tighten one of them, because it just needs to have those screws there to kind of align. And kind of in the industrial world, like if you use a screw to like align something that's very frowned upon, there are much better ways of aligning parts together than screws, which we tend not to use in FRC, but they definitely exist.
Yeah.
Screws are for clamping, not for aligning.
Yeah. This is also another good reason to like use your hole tool in whatever CAD software you use. So like using the hole tool in Onshape instead of just like drawing a circle. Because when you do use the hole tool, you will have these tolerances, or you will be able to like select these options directly, so you don't have to memorize the numbers. I've done enough CAD now to where like I know like 0.196, 0.201, 0.257 off of the top of my head for 1032 and quarter 20. But you guys probably won't want to memorize those numbers. You can if you want, but maybe don't. So using the Onshape hole tool is the way to do that, or to like the way to have that memorized and not have to go look up a table on the internet.
Yep. Use the tools at your disposal. I think I want to stop there. We're not enough to the end of this section. Questions? I don't know if we will have another one of these meetings before kickoff. The plan is to have, there's another shop build day tomorrow. So if you're interested in going to the Pierce shop, Stewart, it's like 12 to 4. Yep, 12 to 4 tomorrow at Pierce. And then Sunday, we will be at the shop some 12 to 4. I think our Pierce students are planning on hosting a mock kickoff from 4 to 6. So that will be something we definitely want to encourage the RHS students to attend. We will be basically practicing a kickoff before our real kickoff. It'll give us the opportunity to kind of go through the motions of learning some rules, making some strategic design decisions, and because we'll be doing it with an old game, it will be very easy to look at robots that were successful and not successful, and basically your decisions can be played out in real time instead of over the course of a season.
Yeah. Mock kickoff.
So
yeah,
stay tuned for that.
2018 is a fun strategy year. Plus, it's a really good simulation of what will happen on kickoff when we get the actual game, and then we have to analyze it really quickly and like figure out what robot you guys want to build. And that's always a fun time. Yeah, because otherwise, yeah, it's a great way to end your season early, or like make poor decisions and then be sad later on. So like getting good practice so you can make good decisions on kickoff and not waste a bunch of time. Because I've been there before, where like the team makes a decision or the team can't make a decision, and then a lot of the robot season goes by and we don't have decisions and it's bad. So practicing and things like that makes perfect and can really help smooth out your robotics experience.
And being able to identify. Rain, what day is the mock
It's
kickoff?
Sunday.
Sunday. Ooh,
We're gonna do it
Um,
after the field build.
okay.
Yeah.
Wait. Sunday after, oh, this coming Sunday. Okay.
Yeah, the second.
Yeah, I got it. Another thing, it's not just not being able to make a decision. Sometimes a team will make the exact wrong decision. I don't know how many color wheel specialists there were in 2020, but that's just a real bad time.
Yeah.
Yeah.
Kickoff's important. It'll set us up for a successful season.
Yeah. We can also do, I guess we can do a future script showcase at some point.
Yeah,
I don't know.
there's a lot of things that we need to do.
Yeah. I don't know. I'll probably make a Chief Delphi post sometime this week, hopefully. Optimistically, we'll see.
So much to do. So much to do. All right. I'm heading out as well. Y'all have a good day.
Yeah.